In this lesson, in lesson 19, and all the remaining lessons for 19, 21, 22, and 23, yes, there are only 4 lessons left. We are so close to the end. And 21 and 22 are basically together, they make one normal lesson size. And all of these last 4 lessons, we're taking the same concept and applying it 4 different ways. The idea behind the concept is this, that I know in the past things have said this, or things have been this, but I think they might have changed. I can run a statistical test based on a sample. I can take a sample from today, and I can run a statistical test based on the results of that one sample to determine if that sample is representative of the wider population. So it's kind of related to what we were doing in lesson 18 for the confidence intervals, but for this one, well, it is called a hypothesis test. For example, somebody tells you that they bowl a 180. Someone tells you they bowl a 180, but you go bowling with them and they score 110, 114, and a 120. Those are pretty low. The question is, do you believe that they just had an off day, or do you think they're lying about their score? Do you think they really they're beefing up their average and they really aren't that good? That's a hypothesis. Your hypothesis in that scenario is, it's not that they're not having a great day, they just suck. In order to test that theory, like I said, we take the results of that one sample and we compare it to what we were told things are supposed to be, and we can run a statistical analysis, again, all in our calculator, and the calculator will spit out a probability. And so we use that probability to say, okay, so if they really did bowl a 180, what is the probability that we would have a sample of 3 games with an average of 115? That's the whole crux of what we're doing. And if that probability is low enough, it's so unlikely to happen that we call, forgive me, shenanigans or BS. The likelihood of us seeing a set of 3 games that look like that is so unlikely that I don't believe you. So just keep that in mind. That's the whole crux of what we're doing, is someone tells you something that's supposed to be one way, but what you observe is something different. We're running a statistical test to find the probability of getting a sample that looks like what we saw, if it really is how they say it's supposed to be. Let's do a couple of examples. Here is the scenario that I was just talking about the bowling. And this week's discussion board is also related to bowling. So remember, the crux of what we're doing in all of the remaining lessons with this hypothesis testing is, just because these games were terrible, does that mean we can declare that they're all terrible, that Paul's game really is lower, his average really is lower, that he's just lying about the 180? All of these are going to have the same step for the next 4 lessons. 4. I keep losing count. 4 lessons. We're doing the same thing. We're coming up with a hypothesis. Okay, we're looking at some evidence, and the evidence is always going to come from a sample. The hypothesis, and I forgot to add this. Okay, the hypothesis is what you think things really are like. Okay, so in our bowling example, you think that Paul has a lower average than 180. We're not trying to guess what his average is. We're just trying to say it's lower than 180. Then we calculate the probability of getting a sample based on if his bowling average really is 180. And then we look at the significance, which this will make more sense when I show you what it means. Okay, so significance is really comparing the probability we got with how sure we want to be. And then we make a conclusion. That conclusion is, do we believe Paul's average, or do we say, nah, it is lower than that? All right, so let's do some examples here. I had asked you, as part of your preparation for the class, to just work through a couple of examples doing these first couple steps. Okay, so as part of this hypothesis process, we have 2 different hypotheses, what's called the null hypothesis, okay, and this HO is how we represent the null hypothesis, and you might hear it referred to as H naught, where that naught is this 0 here. That's what when it's a subscript 0, that means that's your starting point. You'll see that in chemistry and physics and a lot of sciences. The null hypothesis is always that nothing has changed. So what Paul says things were. Paul Bowles in 180. And so our null hypothesis, we can write it two different ways. In English, Paul Bowles 180, here's the English, or we can write it in statistics, and that is that his average is 180. And it always has an equal sign. So there are a number of rules stipulated with this. Then there's our alternate hypothesis. That you'll see two different ways, H sub 1 or H sub A. I'm using the H sub A because I think it's more intuitive, as that's the alternative. Okay, but you'll see some of these videos and some of the readings, they use H1. They both mean the same thing. It's just a matter of personal preference. Okay, this is the statement we're trying to prove. All right, and again, we're not trying to prove what his average is. We're just trying to prove that his average is less than 180. And notice the null and the alternate hypothesis always have the same values there. This is what he claims. This is what I think. Less than, more than, or just different to. Less than, greater than, or just different from. We can just say not 180, something different. And that would be if we just think it's either grown or decreased. We don't know if it's gotten better or worse. We just think that it's changed. Like I said, we're going to be spending a lot of time on this. The main steps are all the same. The only thing that's going to be different is what we put into our calculator. Let's work through this first example. All right, you can see that we have a new variety of wheat has been developed. The proportion, so again, in both of these, like I mentioned last class, like in lesson 18, we're going to be doing all of these two different ways, one for proportions and one for means. And the calculations are different for the sample standard deviations, which means the calculator functions are different. So you've got to pay attention. Okay, so this is proportions. I always highlight that word or circle it or something. So the proportion of seeds that germinate for the standard variety is 80%. And now here's the part that comes next, tells you what that alternative hypothesis is. So the standard variety is 80. That tells us our null hypothesis. Botanist claims the new variety has a better germination rate. This right here, anytime you see someone claims something, what comes next is your alternate hypothesis or your theory. Okay, so that's our HA, and you see that goes here, that it's better than 80%. Statistics, we write P is greater than 0.8. And notice these two always have the same number, always. Okay, and here we're either going to put a P if it's proportions, or a mu if we're looking at means. Okay, so look at B, an automobile manufacturer advertised it's a new hybrid car has a mean gas mileage of 50 miles per gallon. That's our claim, or what we're assuming. And what we're assuming to be true becomes our null hypothesis. Our default assumption is that things are as they always have been, or as someone claims they are. Okay, and our job is to prove it otherwise. Okay, so you suspect, and you see that's another key, that what's going to follow is our alternate hypothesis. You suspect the manufacturer may have overestimated the gas mileage. So if they're overestimating it, our theory is that the average is actually less than 50. And this actually happened with the original Priuses and some of the hybrid cars. They were touting way huger gas mileage than people were actually getting. And then the EPA changed the rules on how gas mileage is determined. Okay, so our statistics version, we're assuming that the gas mileage average is 50 miles per gallon, but our theory is that it's actually less than 50. Okay, so that's step one. Step one, again, is going to be the same for all the next 4 lessons. Okay, so when you're doing this homework, make sure you write notes to yourself and to help you understand whatever it is that you need to do, because we're going to keep doing this for a long time. Okay, the next step we want to do is assess the evidence. The evidence always comes from a sample, always. The sample never goes in here into these hypotheses. These hypotheses are always based on what things were. The sample is what we put into our calculator. Okay, so you're always going to be told information about the sample. We're told in a sample of 800 seeds, 652 germinated. The old one had a 80% germination rate. Ours had 81% germination rate. So really what we're doing with this is that a meaningful difference, or is that just a factor of our sample? And that's really the key of what we're doing here, is our sample showed something different, or our gut shows something different. We're going to take a sample and we're going to see the results of that sample and determine if that's enough evidence to show that the original claim is not true. So in part B, again, we're still looking at that same, these two here are the same ones we just did in number 1. Oops, A and B are the same as number 1. Okay, so an automobile manufacturer advertises that its new hybrid car, again, blah, 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 that part's all the same, but here's our sample. A sample of 30 of these vehicles found a standard deviation of 47 miles per gallon with a sample standard deviation of 5.5. So this is what we're going to put into our calculator. That's our evidence. Okay, the evidence is always the sample. Next thing we're going to do is here's where we put it in our calculator. And this is really what's happening. We're finding the probability of getting a sample that looks like this, assuming the average was 50. If the average of those cars really was 50 miles per gallon, what is the probability that our sample of 30 would turn up an average of 47 miles per gallon? So what we're going to do is we're going to find the probability, okay? And remember, this is our normal curve, so the way we're finding the probability, the same calculations are happening in the background of our calculator in addition to a whole bunch of other calculations. Okay, but what you need to know is it's the same idea. We're finding the probability. This is all the possible results. We're looking for what we call now is a p-value. And it is still a probability, but we call it a p-value because we're using it differently. It's a p-value because we're using that to determine the likelihood of getting a sample like this, but it is still just a probability. And what we know is these 2 standard deviations and up are very unlikely observations. And we already know that. That's a definition from the empirical rule. But for our purposes, we're going to decide, well, how often do we want to be wrong? Okay, and if you remember from lesson 18, we would choose a 95% confidence interval, meaning we're wrong 5% of the time. Now we're doing it the other way around. We're just looking at that 1% chance of being wrong, or that 5% chance of being wrong. That's what we call the significance level. Oh, and here's the calculator functions. I put them in a weird place. I'm sorry. I meant to move them. So make sure you make a note of that. It's under step 3, probability, because you're finding the probability in that step. But you see we have 2 different options for the mean and proportion. The mean has a T, proportions has a Z, and they both end in test because we're doing a hypothesis test. And again, everything is under stat tests. That's where we're going to live for the rest of the semester. So with each of these, what I'm doing is I'm trying to figure out how confident I want to, what level of wrong I can be. Okay, in today's video, it's talking about you want to give your mom more of a benefit of the doubt than your friend with their bowling averages. I'm choosing a significance level, and we call this alpha. This alpha just tells me how sure you want to be. And you don't have to worry too much about this, okay? Those of you with those fancy CE calculators, you can actually tell it if you want a left tail, a two-tailed, or a right-tailed. We're not focusing on this. This is like I'd be a bad stats teacher if I didn't show you it. So I kind of felt obligated to show it to you, but don't worry about it too much, okay? The significance, I'll show you how we're gonna deal with that. Because what we're gonna do is whatever the probability we get out, we're gonna compare it to this level here. And if the p-value we get is smaller than this number here, then we're going to reject that original hypothesis. And we're going to, so reject Paul's claim that he bowls a 180, and we're going to go with our claim that he bowls less than that. Okay, so I have a saying. I say, if the P is low, that HO has got to go. And that's how you can remember it. Let's be honest. I say, if the P is low, that ho's got to go. And so here's where we make the conclusion. If the p-value is less than whatever that level of significance we get is, then we reject the null. and go with the alternative. Okay, so when I'm saying if the P is low, I'm referring to lower as in smaller than our level of significance. If the P is greater, then we don't reject the null. We never accept the null hypothesis. And you'll see a lot of these videos are comparing this hypothesis test to the judicial system. The judicial system never finds anybody innocent. They find them not guilty. Okay, and that's the similar idea that's happened here. We don't accept the null, we just don't reject it. Okay, so let's do an example, shall we? Here's our car example. This is everything we just did. Okay, this was question 1. All right, this was question 2. I'm just going to walk you through it before we do the calculator. Okay, this is all completely worked out, so I just want to show you what happens here. So I put this stuff into my calculator, and here's what I got out. P is 0.003. Okay, so again, we're testing the manufacturer claimed that their cars get 50 miles per gallon. My survey of 30 cars got an average of 47 miles per gallon. The probability of getting a sample that looks like this is 0.003. The t-score, which is basically a z-score, but with a different twist on it, is -3. So the probability is so low of us getting a sample like that, we are going to reject the null hypothesis, which means that there is enough evidence to support that alternative. So our alternative was that they got less than 50 miles per gallon. I'm not trying to say that the cars get 47 miles per gallon. I'm just saying that it's not 50. It's less than 50. Okay, so there is enough evidence to support that the average or mean gas mileage is less than 50 miles per gallon for those cars. Okay, and another term we use is we say that that sample was statistically significant. So even though this is only 3 miles per gallon different, and it's so unlikely that it is a real result, a significant result. So two things that go together. If this P is low and we reject the HO, that means there is enough evidence. Those two always go together. Similarly, if we are not rejecting, then there is not enough evidence. So those two also go together. Number 4 is just the finishing of the second one, the seed germination rate. Okay, so let's do an example together. And so I'd like you to work through this with me, okay? And think about it by yourself as I'm working through it. Read the question, highlight, and circle all the important information. Okay, so the percentage of physicians who are women is 27.9. In a survey of physicians, see now, when you see in a survey of physicians, this right here tells you that what follows is the evidence because it came from a sample. In a survey of physicians employed by a large university health system, 45 of 120 randomly selected physicians were women. Is there evidence at a 0.05 significance level to conclude that the proportion of women physicians in the university health system exceeds 27.9. There are currently, or of the population, 27.9% are women. We want to know if this one specific system exceeds that value. Okay, so think about which one is our null hypothesis and which one is our alternative. Remember, the null is how things are, and the alternate is my theory. I ask you to write it 2 different ways, math and English. It's a proportion, so I'm going to have a P. Remember that HO is always equals. Always. This is how they are. It is 27.9%. But now my alternate is my theory of how it's changed, and that is it exceeds 27.9%. So my theory is that it's bigger than 0.279. Okay, and remember these are always the same. If we write that in English, 27.9% of doctors are women, and we're not trying to be fancy here, folks, okay? So we can just say it's more than 27.9%, okay? And it might be easier to write this English first and then go to here. But you see, we didn't use that survey information. What we're using is this here, the percentage. This says straight up, the percentage of women is 27.9%. Okay, so take a moment and write down, well, what's the evidence? We have a sample of 45 of 120 physicians were women. Okay, so I've just written it in English, but of course we can't put that English in our calculator. We've got to figure out what the N and the X are, right? So this is a sample of 120 doctors. of which 45 were women, which means X is 45. So now we've got to figure out the probability, which means we're going to put it in our calculator. So look back to step 3. This is in the middle of page 2. One thing that will go a long way to helping you remember this is that it's a proportion, which means we're going to have a Z in our name. Because if you can just remember proportions have Z's and means have T's, then that will help you figure out which is which. So given these two, I know it's going to be that one. Let's put it on our calculator. Okay, so we're going to go to Stat, arrow over to Tests, and we're looking for which is number 5, 1 prop Z test. And you can just press number 5 as well. So now it's asking for P sub 0. That 0 coming after it tells you that your null hypothesis, whatever value you put in for there, and for us, it is 0.279. Okay, arrow down, X. I often get X and N confused, so I've got to double check. Okay, X is 45, N is 120. And now this is asking us for our alternate hypothesis. Do we think it's not equal to 27.9? Do we think it's less than 27.9, or do we think it's greater than 27.9? So look back to what we put for HA. We think it exceeds 27.9, so we want the one that's flashing, the last one. I'm going to press enter. And then we can press calculate. Okay, so here's the Z-score. And again, remember, this is the probability of getting a sample that we just observed given the percentage is 27.9. We'll see this p-hat. This is what our sample is. 37.5% in our sample. How likely is it to get such a high number of women in our sample if the true proportion really is 27.9%? That's a Z-score of 2.3, which is a p-value of 0.01. So write those down. I'm going to show you one more thing. Stat. I'm going to go back to this one, 5. I'm going to show you the draw. Remember how we were filling in the normal curve, the area of the normal curve? Okay, never mind. So let's go back, finish this problem then. So I already forgot what Z was. Really, all we really need to know is that P value. But I like to look at the Z value because it just reinforces my findings. We know a Z value of more than 2 is unusual. And in fact, that probability is in fact quite small. So we put in P naught equals 0.279. X was 45, N was 120, and that proportion was bigger than P naught. I always like to write this information to remind myself what I put into the calculator. What's our level of significance? Look back up here, and it's a 0.05. This is the standard kind of default, okay? And what P value did we get? Now we've got to compare these two. Which is bigger, P or alpha? It might be a lot easier if you translate this to a percentage. This is 5%. This is 1%. So which is bigger? Well, the alpha is bigger, which tells us the P is low, so that ho's got to go. When I say P is low, remember that means that the P is smaller than this percentage here, this alpha, this level of significance. Okay, so what are we going to do? Do we reject the null hypothesis? Okay, the yeses have it, and indeed it is a yes. Okay, the reason why it's a yes is because the p-value is smaller. So anytime that p-value is smaller than alpha, we are going to reject it. So that's why I like the saying, if the p is low, that ho's got to go. P is low is referring to smaller than alpha. Ho's got to go is referring to rejecting. And because we are rejecting, that means there is enough evidence. And remember, these two always go together. If we're rejecting, there is evidence. Now we're going to state the conclusion, and that is, there is evidence to suggest or indicate, there's a few different ways you could write this, that the percentage of women in the university health system exceeds or is more than 27.9%. And you see the sentence I wrote, folks? Basically what I did, going back up here, there is evidence to conclude that the proportion of women in the university health system exceeds 27.9%. All I did was take that sentence and added, there's evidence to suggest at the beginning of it, or take that phrase. So that's one full hypothesis test. Definitely not easy. The more you do it, the more you'll see it's the same thing over and over and over. And this right here is probably the hardest part, is figuring out what to put here. And then remember too, the evidence is whatever that comes from that sample. That's the second hardest thing. Let's just spend 5 minutes in groups working on example 4, and welcome back. So we're on example 4, or excuse me, not example 4, problem 4 on page 4, which we did steps 1 and 2 already at the beginning of class. Our proportion, our default proportion is that 80 seeds germinate, but our sample showed that 652 out of 800 seeds we planted germinated. And our theory is that more than 80 are going to germinate. Okay, so we're on step 3 now, figuring out the probability. Did everyone get this? I'm going to press enter. I want to show you how to do the draw, because you don't have to, but it's a good thing to be able to visualize it. So if I go to draw, there is the probability. Remember, and that looks familiar. Yeah, that's what we did, the normal probability. And this isn't a normal curve because it's Z. And here's my Z score, 1.06, and a p-value of 0.14. That's a pretty good probability. Hopefully in Unit 2 you got enough of a sense of what the Z score and the probability tell you that you can see from here that that sample probably wasn't that unusual. It's pretty common. Our p-value of 0.144, we want to compare that to that 0.05. This is pretty reasonably likely though. So which is bigger, P or alpha? Our alpha is 0.05, and this is definitely bigger than 5%. Okay, so that P ain't low, so the HO doesn't go. So we don't reject the null hypothesis. This is the last example we did. This is number 5. Remember when I tried to graph number 5, I got an error? Press Y equals. If there is anything in here, press clear and then enter. We've got to make sure there's nothing here. Also, we got to turn off the stat plots. So go to second, Y equals, and remember that brings us the stat plot. All these other ones need to say off. That's where my error came from. So to turn it off, press enter, arrow over to off, and press enter again, and that will turn that off. And you want to make sure that's off for plots 1, plot 2, and plot 3. Okay, but again, on this screen, you can see which ones need to be turned off. When you go back to test 5, do the proportion, and I can click draw. What's nice is I get the Z-score, and I get the p-value, okay? And I can visualize that probability. So just visualizing this, that's not very likely. And that tells me it might be that I'm gonna reject the hoe. Here you see I drew it here. Okay, I wrote down what I put in my calculator. Our sample showed a probability of a germination rate of 37.5, which is reasonably likely. P is bigger, so I don't reject the hoe. The hoe ain't low. Excuse me, the P ain't low. So I'm not rejecting the null hypothesis. And if I'm not rejecting, that means there is not enough evidence to support the alternative. Those two always go together. So what that means is we do not have enough evidence to suggest the germination rate is higher. Okay, so really what that's saying is that our sample was a little bit more. And I want to point out that our germination rate was, no, that p-hat is wrong. I just want to make sure to point out that the germination rate was 80%. We got 81.5%. You may be tempted to think, well, these are really close to each other, that's why. But there are times, depending on the circumstances and the sample and just a whole host of factors, this might be a significant enough difference. Like the car mileage. Our car mileage example, the manufacturer said 50 miles per gallon. We got 47. That's only off by 3 miles per gallon. But it turns out that was a significant enough difference that it did suggest something was different happening. Okay, so just because these numbers are close together doesn't mean that that's not what's telling you whether we're rejecting or not. It has nothing to do with these being close together, because sometimes that close together is meaningful, that difference is meaningful, sometimes it's not meaningful. Like I said, this concept is going to be coming back again and again for the next 4 lessons, so you'll have plenty of time to get it together. What I'd like to do now is go to part 2 of what happens when we make an error. I want to make sure everyone's clear. There is no way to tell if we made an error. We don't know. We can never know. The test we did was the only test we have. Sometimes the sample's unusual, It may carry out the hypothesis test correctly, but can make an incorrect conclusion because of sampling variability. Okay, and this is what that 1% level of significance comes into, 1% versus 5%. 5% again is typical and the most common for sure, but we set our level of significance lower if we want to reduce the chance of a type 1 error, and we set this level of significance higher if we want to reduce the chance of a type 2 error. Okay, and so you don't have to worry about this part. Okay, that's just kind of more informational for you. What you do need to know is the distinction between these two types of errors. A type 1 error is when we reject the null hypothesis when it was actually true. Okay, so we rejected the null when we should have kept it. Type 2 error is if we fail to reject the null when it's actually false. So we kept the null when we shouldn't have kept it. Let's do some examples that will help kind of illustrate what's happening here. I'm going to keep this there. The key to remember is it has to do with what you do with the null. Okay, type 1 is you reject the null when you should have kept it. Type 2 is you kept the null when you shouldn't have. This happens all the time in the court system. If you're paying attention, you know this. So our null hypothesis, innocent until proven guilty. The alternative hypothesis is that the person is guilty. So a type 1 error would be that I think they're guilty, but they're actually not. Okay, the consequence is that the innocent person gets punished. I think that many of us would agree that the courts tend to make type 1 errors, especially if you're a black or brown person. Innocent people get punished all the time. Think about what a type 2 error would be in this example. What would be the consequence? A type 2 error would be they did it, but they get off scot-free. That would kind of be more the consequence, but what would it actually be? It is that I think they're guilty and they're not. Oh, excuse me, I think not guilty, but they did it. Okay, it's oftentimes easier to think of this first, the consequence, than it is this one. This one's a little more harder to wrap your head around. Okay, let's go on to number 7. Let's talk about sick kids. The child is seriously ill is our null hypothesis, and our alternate is the child is not seriously ill. So what would be a type 1 error, and what would be the consequence? Let's just focus on the consequence. It kind of makes it a little easier. What would a type 1 error be in this scenario? What would be the consequences? Anyone?
Like the child doesn't get the treatment?
Yeah, exactly. Because I think the child is not seriously ill, but they really are. Okay, because I reject the hoe incorrectly. So I don't think they're seriously ill, but they are. Okay, what about a type 2 error?
The child gets unnecessary treatment.
In the type 2 error, remember type 2 is when I kept the null and I shouldn't have. And so that is that I think they're seriously ill, but it turns out they're not. Okay, and unnecessary treatment could be really bad. That could be like someone going through chemotherapy unnecessarily. The type 2 error would be, oh yeah, that's what I just said. I just didn't write it down. My iPad stopped sharing. Let's go into this one. This is one of my favorite ones because this is me and my husband in a nutshell on number 8. The food is safe to eat versus not being safe to eat. I cannot tell you the number of times that man has gotten food poisoning because I looked at something and I said, that does not look good. I don't think you should eat it. And he's like, no, it'll be fine. For example, I am not joking. Every single time we go to Laos, he's gotten food poisoning. Let's see, I think that's been 3 or 4 times. All but one of those times was airplane food. And I looked at it, I said, this sandwich looks really terrible. I am not going to eat this sandwich. And he goes, not only will I eat mine, I'm going to eat yours too. And then he got really ill. Right. So my husband and I make type 1 and type 2 errors all the time. Let's switch this question up a bit. I'm gonna give you a poll. Okay, look back at the definition. Type 1 error is you rejected the null when you should have kept it. Type 2 is you kept the null when you shouldn't have. He thinks the food is safe to eat, but it's not. That means he kept HO when he should have rejected it. Is that a type 1? That is type 2. Okay, so now I'm more prone to go the other way. If I throw out food I'm scared of, but it turns out it's okay to eat, for instance, putting away groceries, last week, 3 days later, I found some orange juice that should have been in the fridge. It was still in the cooler. I was like, oh crap, is this still good? And of course, so you know what happened is I wanted to throw it out, but my husband was like, nah, it's fine. It'll be fine. I was like, okay, you have some and I'll wait a day and we'll see what happens. That is a true story. That really was just like 2 months ago. It was fine. But I'm not kidding. I really did like, you drink it. And I waited the next day and he was still fine. So I was like, okay, now I'll have some. So if I throw out food that I'm scared of and it turns out it's actually okay, is that a type 1 error? Go back to which one of these is the null hypothesis and which one's the alternative. The food is safe to eat, but I didn't think it was. I rejected HO when I should have kept it. Okay, is that a type 1 error? This one is a type 1 error. I mean, this is true that I tend to make type 1 errors and my husband tends to make type 2 errors every time we go to labs. Every single time. We're going to be coming back to this topic a lot. The next 4 lessons are covering the same thing, but in a slightly different way. We're going to look at 3 other different scenarios. This is just kind of the basic scenario. Remember, the key of all of this is how something was. My sample shows something different. Is there enough in this sample to suggest that the way things were has in fact changed? We're doing everything in our calculator. And then also remember, if that P is low, that HO's got to go. The P is low, we throw out that HO. This is where we get to all be pimps. The next 2 lessons, remember 21, is we're doing this with 2 different samples. We do a sample twice. Or we're comparing, for example, if we're comparing on-time flights for Delta versus on-time flights for American, is there a difference between those 2? 21 and 22, instead of comparing what happened in the past to what happened currently in my sample, what I'm doing is I'm comparing 2 different things to say, are those percentages statistically different from each other? Are Delta flights really more statistically on time than American flights? Are there statistically people more likely to support Biden versus Trump, right? It's comparing 2 different samples of unrelated things. And then in 22, we're doing that same thing, except we're going to add a 3rd one. Here we just did past and current versus what I see in front of me. And then the next 2 are comparing 2 different samples to see if there's any distinguishable difference between them, statistically speaking. With that, have a great rest of the week. Don't forget, I'll be sticking around